So, we have to finish up with the calculation of the heat capacity and move to magnetic properties. So I'll just write down a few things that we need in order to fit. All of them we discussed in the previous lecture, but just so we will be able to use it. So we had this integral. We spent quite a lot of time developing. Okay, we spent about an hour to get to this point. We had the calculation of sorry.
G prime
Excuse me? Here, yeah. Okay, which we used in order to calculate mu. This is just writing this integral in the case of h equal g. And there's some mathematics. We got mu is essentially the Fermi energy, not surprising, with a correction. Okay, so the main point is mu is E for me, of course, when t goes to 0, and has a correction proportional to t squared as the temperature increases. But as long as all our assumptions of the development of this integral are correct, meaning t is much smaller than E for me, this is also a small correction to mu. And we were left with the calculation of U, the energy per volume was which we will do now in order to conclude our calculation.
Is it mu here as well?
Excuse me?
Right. Is it minus here as well?
Here?
The integral and the... Or maybe there should be a plus.
Let me check. The integral has a plus. We get the minus. Look at our calculation in the previous lecture. You'll see from where the minus comes out here. Because we wrote here. Here it should be a plus.
Okay, that was my question. Okay.
Okay, so let's write down explicitly. Okay. So how did I get to this point?
What happened to the mu?
This good? It's in here. That's what I want us to follow. Okay, so that's the final result. Let's see how we get it. Okay, so we have to do this integral. And we have to add this part. Someone can see what we're doing here? Where should we start? Okay, let's start with the easiest part.
What are we trying to
Shows that this is correct. Okay? Just wrote down the development of the integral. Okay, so
integration by parts maybe?
let's do it one step at a time. Basically, what do we have here? We have here several points where mu appears, right? We use this relation and stick it into this calculation. Okay?
So the first term with vanishing, we are only left with the second part, right?
Which first term?
Everything in the parentheses, the brackets.
Let's look on it for a moment. Basically, you are almost right. Basically, what do you need to do here? Plus am I allowed to write it? Always. So basically the first term with EF we have already performed, right? We did it for the t equals 0 case. Now we look on the second term. Is there a big change between mu and EF?
No.
No. So what can I do with the integral at that point? You can assume that GE could be replaced with GEF, and E could be replaced with EF, and all I have there is mu minus EF. That is the additional terms that I get. Okay? Now, when I have mu times G prime mu, I can also replace it with EF. G prime of EF. Because the second correction will give me a... Sorry about this, here I'm missing... What am I missing?
KBT squared.
Right. So, I have already a contribution of order t squared. Anything that comes from mu or g mu will be a contribution of order t to the fourth. Again, I can't forget about it. Same logic here. So after summing up everything, I'm left only with a contribution of order of should have all this comes out 0, and this is the whole contribution. So, at the end of the day, the contribution to CV, to the heat capacitance, is of the order squared T times, and when I substitute GEF and this is the most important thing, the contribution is small, because the temperature is much smaller than E Fermi. Now, as I said at the beginning, we could get more or less to the same conclusion just on looking on the physics of the problem. There's only a small shell of states at the Fermi surface for which the occupation can change as function of temperature. We did the whole calculation in order to get a more precise result, but we didn't get anything that we couldn't have guessed before. Still, it's useful because this type of calculation appears in the calculation of all kinds of quantities in solid state physics, so it's worth to once in your life see the full calculation in case you'll need it for a specific quantity that you're interested in. Okay, so that's the first clue that we have here. Quantum the electrons in a metal behave like a quantum particle. They contribute much less to the heat capacity than you would have guessed from classical particles. Not all of them contribute. Only of order of kBt over E Fermi. Of course, at large temperatures of order EF, you're back to the classical behavior. All of them contribute.
Why does it mean? Why can we conclude that they are quantum particles?
Because if I know nothing about them, right? What should be the contribution per? Here we are looking on the contribution of electrons per volume, right? What should be the contribution? The density of electrons times kBt times 3 over 2 or something like that. Not kBt over EF.
Why do we conclude that because of quantum behavior? Why is that the clue?
Okay, what happened here at the end of the day? All the heavy mathematics, what was it based on? Remember that we had at some point of the development dou F to dou E. the change of the occupation as function of energy. Classically, this is a very broad function, right? Because you have more, the change in occupation is a well-behaved continuous function, right? What is the difference in quantum occupation of fermions?
Pauli exclusion.
Pauli exclusion principle. You have the raster. The fact that you have a stir comes into the fact that you have contributions only from the region of the Fermi energy, which brings you to this lovely behavior, which tells you that mu is the whole contribution comes from particles close to. Only they can contribute, and at the end of the day, the reason is very. What is essentially the role played by the Fermi energy? As long as you're not too high temperature, you have some occupation, right? Now you have an electron sitting at a value of close to 1, and you want to give it a small amount of energy. Why a small amount? Because it gets it from the heat bath, and the temperature is much smaller than E Fermi. Meaning it can't take kBt from here. All it can do is try to move a bit. Right? If I didn't have Pauli exclusion principle, try to move a bit, lovely, no problem. If I'm a fermion, no thank you, I don't have where to go with this energy. It's not useful to me. I'm stuck. Who can play with this? The guys here, because here a small movement puts you to a state that is from almost occupied to almost empty. Oh, that I can get. That's fine. So instead of looking on all the states occupied of order of E Fermi, can look only on a small window of order kBt, because these are the only guys in the game. So how many guys I have in the game? kBt over EF, which is the conclusion, which we saw for the game played by the chemical potential, mu, and we saw also for the heat capacity or the energy. So this is a very strong quantum, not in the meaning of Schrödinger equation or waves, in the meaning of Pauli exclusion principle, which is also a quantum concept. Okay, another influence of Pauli exclusion. All solid state, or if you want me to be more explicit, everything that you see around you, all material as you know it, is a manifestation of Pauli exclusion principle. When materials stop to behave like fermions, very interesting things happen. You have superconductivity, you have superfluidity, you have very high temperature, so you have plasmas. But your daily life is ruled by the Pauli exclusion principle. The fact that you're sitting here and not going through the floor is Pauli exclusion principle. All chemistry is built on these electron shells and how they combine together, Pauli exclusion principle. Otherwise you could, no one would care how many electrons you have in a shell if you don't have Pauli exclusion principle. And now we'll move on and see that actually all magnetic properties depend on it. Magnetic susceptibility. In general, in physics, what does the name susceptibility mean?
The capacity of a material to be influenced by a field, like the response to the material.
I like better your second part. The response of a material to an external influence. I start a magnetic field and I want to see what is the magnetism. Conductance, I start an electric field and I want to see the flow of electrons. Basically, I kick the material and want to see what is the response. And usually, when I kick the material, I don't kick it too hard. I put a small magnetic field, a small electric field. That is the basic response that I'm looking for. Could be that higher will be more interesting, but unless I specify when I say susceptibility, that's in the limit of the applied field goes to 0. Okay, so magnetic susceptibility is I turn on a small magnetic field and want to see what is the magnetic response of the material. Now, here we are going into something that happens a lot in solid state physics. We're dealing with complicated materials. They have components. We have the ions, we have the electrons. We could have ions that have already a magnetic moment. We could have a magnetic moment because of the electrons. In this lecture, we will talk only about the response of the electrons. We will not touch upon what do the ions, how the ions respond to the magnetic field. Okay, so we simplified our problem. But even for electrons, we have two totally different ways that it can respond to the magnetic field. Someone can guess?
The orbital and spin.
Right. Spin is a magnetic moment. So we know from the time that you were able to reach to the fridge door and pull down some magnetic things that was attached to it, that basically if I have a magnetic moment, I can have a response. But there is another mechanism that you know from high school where I have a magnetic response, which you use in electric motors and so on.
Moving charge.
moving charge also creates a magnetic. Once upon a time, it was believed that the movement of the charge, they thought about an electron as a small ball of charge and it spins and you get a magnetic moment, but we nowadays know that that is not the explanation. It's a intrinsic magnetic moment that comes out from Dirac equation. It's a relativistic effect, but has nothing to do with current. So basically, when we're looking onto what can happen to a system of electrons, and see, we're continuing with the same simplifications that we did for the heat capacity. Electrons are just electrons in a box. We don't care about the lattice, we don't care about the ions, we think about it as a box that only keeps the electrons in place, but nothing more. Nevertheless, we have two different responses that can come out of applying the magnetic field. So, we have a response due to spin. Generally called Zeeman effect. Zeeman is a Dutch physicist who investigated it. And we have orbital effects coming out from the fact that the electron movement exists due to the magnetic field. Okay, let's start with spin. Okay, classically we know what happens. Give me the magnetic field.
B scalar times Z.
I could, if I choose a direction and I'm not out of my mind, I decide that it's in the Z direction. But in general, I can point B anywhere. Sometimes I'm not just writing Z because in certain lattices you can talk about even two-dimensional systems. Can put B this way and this way, right?
So an anisotropic effect.
I mean, but intriguing. If it's this way, then it would only affect the spin.
Right, and that's a very strong experimental technique to separate the orbital response from the spin response. Because for the spin, the fact that you're putting it here or here doesn't make any difference. At least for the simple model that it's electrons in a box. For the orbital, it makes a whole difference in the world. So if I go and take a measurement at different angles, I can tease out what is the orbital and what is the spin effects that I measure. That's important. So therefore I just write B vectors times S. So what is basically the effect of a magnetic field? The energy comes with a minus. So what does it mean?
That it's a spontaneous process.
Well, of course, but what does it mean on the direction of the induced magnetic field? While for electrons without a magnetic field, the spin can't take any direction because it doesn't make any difference. If I put a small magnetic field, they will all go in opposite direction to the induced magnetic field. Okay, so classically, the effect of spin is very clear. Put in a magnetic field, I'll get a response of a magnetic field in the opposite direction. How strong will it be? Depends on G and mu B. G is close to 2, but not 2 necessarily. And mu B is the permeability of the system. Okay, so it seems we have nothing interesting to study.
So we are neglecting the spin-spin interaction here because due to the magnetic field it's...
Because the same reason that we threw out the Coulomb interaction that is much stronger. Right? We said the electrons have an energy of h bar square k square over 2m. You should have then pelleted me with stones and say, sorry, electrons have strong Coulomb interactions between them. We neglected that and we neglected here. We look as if each electron is individual in response to the magnetic field individually. Is it true? No. Is it completely wrong? Again, no. It's a good approximation. To understand it, graduate course. So just let me define susceptibility. Usually denoted by a chi. That is very intuitive, the change in the magnetic field of the system due to the external magnetic field. And I don't even want to go into the thermodynamic relation that I have here regarding the free energy. I'll talk a bit more about it when we'll get to using it. Okay, so the classical picture at B equals to 0, each electron is pointing with its spin wherever it feels like. Now for you, let's say BZ. Let's put a field this direction. Well, not exactly temperature will, but at low temperature all of them will order in an opposite way, right? Because the energy has to be minimal.
We're talking about paramagnetism in the zero field, right?
For Zeeman effect, all you can get is paramagnetism. Sorry, Diamagnetism is the other way around. Para is in the direction of the field, dia is opposite. Well, we didn't introduce it yet, so... Is this picture correct in the quantum limit? Hell no. Why? Okay, let's go and look on our model of an electron in a box. You know what? Let's make life easy. Let's look on it on a one-dimensional system. Okay? So, let me do it this way. Actually, I don't even care if it's one-dimensional or whatever dimensional it is. I have states. Okay? How do I fill up the states at t close to 0?
From the lower one.
I'll start filling them from the lowest. Let's say I come with the spin up. Then I'll fill one with spin down. Why not put spin down in the excited state? Because it costs energy. I said we're at t close to 0. So we'll have this structure, and here we'll have this structure. Okay. How much will I fill? Go according to E for me, right? I switch on a small magnetic field. These guys are happy. These guys are unhappy. But as long as it's small, if I'll switch this guy, now let's assume we have some finite magnetic field. What will this final magnetic field do? Each state that was previously whatever will get a lowering in its energy for the downspin and a heightening up in the opposite direction. So all these states that were previously like this are now like this.
That's the Zeeman effect, right?
That's exactly the Zeeman effect. But here I want to emphasize another point. Let's say I had two filled up states in the beginning. So the first electron coming into the system comes in here. Okay, that's the lowest level. The next one, which according to the classical description should be also a spin down, says 1 minute, I'm ready to pay the additional energy of being with spin up, because it's still cheaper than going into the next state with spin down. So basically nothing happened. strictly speaking, if I'm defining the susceptibility of a system as the behavior at B going to 0, and the system is finite, susceptibility is 0. Here I had an almost immediately switching of all moments, all spins. Here I have 0. Completely different behavior. Now, this is a picture that you wouldn't hear in the classroom 20 or 30 years ago. Why? This picture is built on an intuition of a small finite system. Okay, where this difference is large. For large systems, the level spacing for a big system is very close to 0, and the order of limits, is this going to 0, or the temperature is going to 0, and or B going to 0 becomes important. And usually it's smeared out in the consideration. But nowadays, when we can build nanoscopic materials, you can actually see this game. Actually, moreover, it can immediately tell you if you have an even or odd number of electrons in your system. Why? Because if you have an odd number of electrons, let's say you have here another electron, if it's up or if it's down, it's a fluctuation, it doesn't really matter. Put on even a very small magnetic field,
And there will be susceptibility.
and there will be susceptibility. It's small, it's a susceptibility of 1 electron. It's hard to measure, but go to Bina and she'll measure that for you. So things change. All the caveats that I told you, it has to be a magnetic field larger than the level spacing, you won't find it in Ashcroft because it's not interesting to Ashcroft, because for a large macroscopic system, the level spacing goes to 0 as the magnetic field, as the temperature. Okay, but just keep it in mind. Not everything, if you go and do research nowadays, is exactly what you see in Ashcroft. Okay, so Pauli susceptibility, which is exactly this picture. But at the limit of large systems. Okay. What is the total magnetic moment of the system? The magnetic moment of a single electron times the number of electrons that have their spin up minus the number of electrons that have their spin down.
Are we assuming low temperature?
Yes?
Then it would be either 0 or -1.
What is 0 or -1?
Like minus.
No, that was under the assumption that the level spacing is finite. I told you that now we're going back to the world of, it's not classic, macroscopic. It's quantum but macroscopic. What do I mean by macroscopic?
You have a lot of electrons.
I have mainly the level spacing is always proportional to 1 over L to some power. L is the size of the system. L goes to infinity. The level spacing is almost 0. And you start to discuss here, as usual for questions of susceptibility, order of taking the limits to 0. Okay, we'll do it exactly. At b equals 0, the density of states, and I'm talking density of states and not number of states, exactly because I'm talking about a macroscopical system. The density of states with up at the Fermi energy is the same as the density of states with down. B different than 0. Why is this direction of plus minus?
Because the lowest level is filling up, the down level is filling up.
Sorry for erasing the previous system, but let's draw the states. Now, the down, let's assume that this represents the density of states of the up, this of the down. I put a magnetic field. The down goes down in energy, the up goes up in energy, meaning that if I'm putting the Fermi energy at some point, tells me till where did I fill it up, this guy is in the higher, the down is in a higher point of the usual density of states than the up. Therefore, here is a minus, here is a plus. So, what is the number of electrons? Let's do different colors. As we have learned, And now I reintroduce temperature. Again, I still assume that the temperature is low compared to the Fermi energy. If it's large compared to the Fermi energy, no problem. Everything is filled up. Everything points in the opposite direction. I don't have to think about it. Okay. So, I want to rewrite okay, what do I do here? Susceptibility. B is small. So what do I do?
Expand.
Expand it as usual. What did I forget? Almost correct.
Upside down.
Hmm?
Okay, fine.
Derivative. Now, just Now, just for notation, you remember that we defined the G for the two directions of states. Here we are using one direction. We'll put half just to be consistent. Okay. This is the same for both of them. Okay. Derivative by parts, integration by parts.
Minus.
Okay, let's get a feeling for t equals 0. What will be do we at the Fermi energy? Correct, because it's a step function. Okay. Susceptibility mu b squared times number density of states in E Fermi. For a real finite system, there's no density of states in E Fermi because E Fermi always sits between the last occupied and the first unoccupied state. For an infinite system, it's a meaningful concept. Okay, so that's Pauli susceptibility. And we can put in GEF as we have met. So it gives us just inserting the value of the density of states at fermion. Good, so that's the response of the spin. Pauli's contribution, which comes out of Zeeman effect. And it's paramagnetic because plus, why is this plus? Because of this definition of minus here. It's paramagnetic. Para well, those are opposite because the definition with the minus end up with the plus. Okay, orbital. Now well, not sure we'll finish in this lecture, but matter it's really a nice calculation here. What happens when I put in a magnetic field? I want to calculate electrons in a box, and I had this lovely operator, we're in quantum mechanics, right? Solved it and got the results. H squared k squared over 2m. What happens if I put in a magnetic field?
The four moment, the four potential.
I have to correct my Hamiltonian. Now, you have seen it, and from my experience, almost no one remembers it. Putting in the magnetic field
Why is there a dot over the P?
it's not a dot, it's a hat. It's an operator. In Hamiltonian's way of writing mechanics, putting the magnetic field is replacing it by the momentum minus some constants times the vector potential.
So it's not.
In a uniform magnetic field, you can do a transformation to make it a function of K. Then you just get a harmonic oscillator over K.
And we'll do it exactly. If you have seen it, I'm sorry that I'm boring you, and if we did, most people haven't seen it, and it's actually a cute transformation.
It's like the one place where the transformation is like really useful.
Right. So that's why I'm bringing it, except for it's useful for its magnetic field.
So instead of having the mechanical momentum, we have the generator of translations, right?
you can look on it this way. You can say I'm incorporating into the momentum the influence of the magnetic field. Why? Because take this guy, do the usual Hamilton equations of motions, and you will get the equation Lorentz force out of it. So at least classically it works. Quantum mechanically, as usual, take the Hamiltonian and call it an operator. Right, so anywhere that I had something is replaced by the operator of something. Okay. Let's talk about a specific case. I want a magnetic field in some direction, not wanting to be insane. We'll choose it in the z direction, but it really doesn't matter because it's a three-dimensional system. But I don't need B. I need A. Okay. In principle, I can replace it by any A vectors that gives me B. You know that there are an infinite number of possibilities. The only thing I have to worry about is that my final result, any physical result, will not depend on A, on the gauge that I chose for A. Can the wave function depend on the gauge?
No. It's on the face, like you have to put it on the face.
Yes, it can depend, but any physical quantity that I calculate with this wave function should depend. So it's a small distinction, but important. The wave function is not gauge invariant because it doesn't represent any physical. The easiest way to see it, take any, let's say, a free electron wave function and multiply it by a phase, a constant phase. Nothing happens. It's a different wave function if you write it down in every point, but it doesn't change any results. Same here. So I'll choose a gauge that will be convenient for me. So and I won't even choose a symmetric gauge. You'll see why. I'm choosing only AY equal to something, or the AX and AY are equal to 0. Why? Because I can. Remember X, Y, Z.
X to Y to Z.
Works. Okay, so it's a kosher vector potential, not symmetric, but so let me write down the Hamiltonian with the specific gauge. Vector potential with this gauge. Okay. Because the x component and the z component of A is equal 0, so nothing changes there. Nothing more than inserting the vector potentials that I have chosen. Writing down the Schrödinger equation. Didn't do anything except writing specifically down the equation. P is I, H bar, go to do Y. Don't have, you'll see in a minute why I separated the minuses, but that's not important. Okay, how do I go forward with it? I'll guess a form of a solution.
So we can ignore Z.
No, we can't ignore Z. We can immediately guess the solution for Z.
Z is just a free particle along the Z-axis.
Both physically and mathematically, this almost begs us to put in this solution. What comes perhaps as more as a surprise this guy. Because
I can mute.
Because look, what happens, the complication actually occurs not in y, it occurs in x. The fact that we have here a potential which depends on x. For y we have here something, but let's see how it acts. So if I guess the solution, I just put it in and see what is my new equation. So, this is trivial, that's what we expected.
Shouldn't it be positive?
What should be positive?
Shouldn't it be positive h bar squared?
No.
That's not
Just a moment. No, here, yes. Okay, because it's here I have no dependence on these guys. That remains the same. Okay, here the dependence on y will pull me down a minus ky squared. Okay, so we have this equation to solve. Okay, sorry, one small mistake. It's not. It's phi, it's not. So all the e to the power ikx, kzz and ikyy dropped off the game. Okay. Can anyone guess what equation is this?
a harmonic oscillator.
The harmonic oscillator, our good old friend from quantum mechanics 1. Why? Because I have x squared, so it's moved by some constant. Who cares? Second derivative, another constant. Who cares? So we have to organize our terms here, and we'll get a solution pi of a harmonic oscillator. We'll do the details in the next lecture, but what is the physics here?
The electron is spinning around the point.
So in one direction, you have basically a harmonic oscillator motion. Classically. Quantum mechanically, you have the equation of a harmonic oscillator. And this will give us a bunch of interesting results, including what I told you about the Hall effect, the fact that it can be quantized, quantum mechanics. All is hidden in this simple equation. Okay, so we'll see it in the next lecture.
Thank you.